it. I'm just going to get started because there's a lot to cover. So I'm going to cover three main topics. So like, what is quantum gravity? What is Monte Carlo metropolis? What is the Ising model? Luckily, Carter already covered Monte Carlo, so I'm going to glance over that. And lastly, the Freeman algorithm, named after Walter for its who invented it. So we're going to get to that. It's all very interesting. So what is quantum gravity? So quantum gravity is pretty much just what it sounds. We're trying to unify quantum mechanics and gravity, and that is not easy. And we have to do that because while both these theories are great, in certain scenarios, we have to think about both of them together, especially around black holes. And black holes, as it turns out, are solutions to Einstein's equations, and they are real. So I've included a picture of a black hole. That looks really cool, just because this is something that's out there, and we need to think about. Also, dark matter is kind of a mystery. It's gravitational, and it's probably some sort of matter, which means quantum mechanics needs to describe it. Whether or not you really need quantum mechanics to describe it is up for debate, but either way. Also, cosmological inflation, the universe, the early universe, expansion. We need to solve these problems. And physics has progressed when we unify theories. Electromagnetism unified electricity and magnetism and showed us what light and what optics is, that light and optics are part of this electromagnetic spectrum. General relativity united Newtonian gravity and special relativity and gave us four-dimensional space-time and curvature and black holes, it turns out. And quantum field theory united quantum mechanics, which also united some things, and it united quantum mechanics with special relativity and gave us the standard model and particles and all this. And potentially the graviton, which is a quantum mechanical particle that mediates the gravitational force, which I'm not going to talk about too much. But I want to talk about quantum mechanics and specifically the path integral. So a path integral is a formalism for doing quantum mechanics and invented or discovered by Richard Feynman that says if you want to know the amplitude from a particle to, let's say a particle to go from point A to point B, like classically, if you throw a ball, it's going to go on one path, and we're in 211, we can calculate that path. But quantum mechanically, that electron or ball will take a number of different paths, and it could take all of them at the same time, really. We have to sum over an amplitude for each one, add up those amplitudes, and they can interfere, and we get complicated behavior out of this path integral. And this really gives us a beautiful interpretation of quantum mechanics, which we're going to use, which quantum gravity and quantum field theory especially takes full advantage of. So this is the formal definition of a path integral for quantum mechanics. And on the next slide, which is going to be very technical, and I'm warning you that it's going to be the peak technical slide. And we're going to see what gravity looks like in this formalism. So if we do something, so you notice on this last slide, there's an I here. So if we do something technical called a Wick rotation, I'm not going to get too into it, we can pick up we can basically evolve an imaginary time, and we get something called the partition function, Z, which is a path integral too, just no I, but in a minus sign. And this term S, the action. So for gravity, we integrate really, instead of like all paths through space that a particle take, we take integral over all space-time configurations that space could have. And we add up the amplitudes for all of these paths, and we get something called the partition function. And in this case, this is using the Einstein-Hilbert action, which is the gravitational action, which incorporates factors like G, so Newtonian gravity is in here. We have the metric G, so this is general relativity. We have R, which is the curvature of space, and we have lambda, which is the cosmological constant, which has to do with inflation. So we're trying to model all of this in a quantum mechanical way. And since space-time is four-dimensional, we need to account for that too. And we need to put this thing on a computer, so we need to discretize space, and we need to think about a clever way to do that gets out the dynamics that we want out of a space-time. So the way that Professor Leho here does that is by modeling space as a bunch of triangles, basically, or generalizations of triangles called simplexes. So a zero simplex is a point, a one simplex is a line, a two simplex is a triangle, and a three simplex is a tetrahedron. And then a four simplex is a four-dimensional version of this, which I can't show you. Well, you could look up a picture probably, but it's hard to visualize. Anyway, when we put this on the lattice, instead of summing over all spacetimes, we sum over all triangulations, T, weighted by some factor c of t, and this other factor which has to do with the order of each triangle, how many triangles it's connected to, other tetrahedron. And the important thing is this factor here is a global factor that has to do with the whole space-time geometry. And then we have this Einstein reg A action, which is what weights each configuration. So this global piece is going to come into play later. So moving on. So I warned you, it gets technical, but it's gonna get cooler. So this is what this looks like when you put it on a computer. So in a certain sense, this is what our universe model is. We have our triangle, our simplices, and they're all connected to each other. We have one simplex connected to another simplex, and they're connected. And we start out with some simple, like spherical-ish, four-dimensional shape, and then we evolve it. We randomly pop some simplexes out, create some simplexes, delete some simplexes, add in simplexes, and we get these sort of universes that arise. And in like a coarse lattice, we get this kind of lumped up universe with lots of branches coming off of it, which you call baby universes, which isn't so great. We want our universe to evenly fill space and to be uniform. So as we start to like bring down the lattice spacing, so go back down towards the continuum, we get like more uniform spacing. So these are two configurations here which have more uniform, fill up the space more uniformly. And this is one up here. So each of these are simplices, and it's hard to see, but they all connect, but it's pretty beautiful. And I think these are 4K simplices. There's 4K, and this one's 8K. I think I might be getting that wrong. It's hard to tell, but these look pretty cool. And this is kind of what's going on in the computer. So now Monte Carlo, Metropolis, and the Ising model. So how do we evolve this? We need to randomly flip things, so we need to figure out the probabilities of how to do that. So I think Carter already talked about Monte Carlo, Metropolis. So this is a short kind of derivation of the Monte Carlo or the Metropolis-Hastings algorithm, which I'm not going to go too far into, but basically we're interested in finding transition probability. It's the probability to transition from one state A to the next state B. And we know the probability to be in a certain state is given by the Boltzmann distribution. So it's Boltzmann distributed by this e to the minus beta, the e to the action, essentially. So there's this certain condition that has to be satisfied. This probability of going A to B over probability of B to A has to be equal to this. And one solution is this function pi AB, that's the minimum of 1 and e to the change in action. So what this says is change in action is basically change in energy. So if our thing increases energy, then the probability of going to state A to B is going to be e to the minus something positive, which is going to be small. And if the change in action is negative, we go down in action, down in energy. Then e to the minus is positive. This is big, so we take the minimum, which is 1, so we're just guaranteed to go to a lower energy state. So that's an overview of that. So the Ising model. The Ising model, again, I'm going to try to breeze over this. I want to get to other things. The Ising model is about spins. So you have a lattice of spins that can be up or down, two-dimensional, and we're interested in finding like configurations of this lattice and the energy of the lattice. So we can flip a spin and we can increase or decrease the energy. So the partition function basically says it weights each state by like if you're in a state, it weights all the other states by the action that'll happen or the change in action to go to the next state. And T is the temperature. It's a model for a ferromagnet, which I can talk about more if anyone has any questions. But you can assume you can look at Wikipedia if you want to look up the Ising model. I'm going to show an animation at the end. I should detail that. So the Freeman algorithm. So this is our answer to a question about, so the Metropolis algorithm had some chance that you would reject like a move. So you would look at a move, you'd pick a random site, you'd say, what's the probability of flipping it? And you could not flip it. So that's kind of a waste, especially when you have a really low probability of flipping. Like our quantum gravity stuff has really low probability of flipping states. So we'll spend a lot of time doing nothing. So we don't want to do that. We want to do stuff. We want to flip things. So the Freeman algorithm is an approach that eliminates rejections. So to do this, we pre-compute the probabilities for each move. And then we compute and we put those numbers in a list. And then we can compute another list of numbers where we sum up the we sum up the probability from P1 to that probability, and we put those numbers in a list. And then that gives us kind of like imagine a bookshelf where each book has a different thickness, and that thickness of the book is like the probability of going to that state. So all of these moves are possible. So what we can do is we can say, all right, the bookshelf, all these books have a certain length, and we can say, let's just pick a random point on the bookshelf and pick that book and make that move. And like the bigger, thicker books were more likely to hit that book, and the really small books were really unlikely to hit that book. So that's the essence of the algorithm. And we can do that, and we can put it on a computer, and we can also calculate like a number that tells us how many like Metropolis moves we really rejected, and that's what this n reject is here. So perk. So this is good. So a perk of this is we can very efficiently implement this using binary trees. So binary trees are a computational data structure that allow us to to find probabilities, search the bookshelf, and update the bookshelf very quickly, and that's great. The problem is, going back to the Lattice quantum gravity partition function, is we had a global term, and our probability pi AB that we came up with was capped. It was capped at 1. So if we want to update those probabilities after each move, we can't really do that because there's this global factor in there, and we have to. It's very not obvious how to do this, and we never figure out how to do this. But if you satisfy the detailed balancing condition, is also satisfied if you take the square root of the probability, or e to the minus delta s over 2. So if you say pi AB is equal to this number, which is not necessarily less than 1, we call it a ponderance, which has it's a word that means weighting, basically. It's called, we think of it as an uncapped probability, in quotes, 'cause not really a probability. We can efficiently put this on the computer, and then we can factor out the global factor and do everything we want. So that's great. So I'm going to show on the next slide. So this is really a visualization of the Ising model and the difference between Metropolis and Freeman. And each of these, they're going to run at the same time, and they're going to run the same amount of steps. The Metropolis is going to make rejections, and the Freeman isn't. And we're going to see just how fast this one on the right thermalizes relative to the standard Metropolis algorithm. So let's take a look. So you can see this one's already gone to a thermalized state, and this is like a magnet, like magnetizing. And like if it gets cooled down a magnet, all the spins will sort of align, and you'll get this magnetized object. And the one on the left, the Metropolis, took some more time to get there. And that's about it. I think, how am I doing on time? Am I still there?
You're about out of time.
Okay. So
we have, if you want to make some concluding remarks, and then we have time for a couple of quick questions.
All right, I'm done. So I think I'm good if you guys want to ask questions.
All right, so let's thank Aaron for his talk. If you have questions, then step to the left of the podium in front of the audience, and you may then speak to everyone, including Aaron, and ask him your questions.
Yes, and I can't see, so please speak up if anyone has any questions.
Or you can type them in the chat, and I will read them to everyone.
Perfect.
While we're inviting questions, is our next speaker Jackson here? Oh, there is Jackson. So Jackson, you're on deck. So I have a question for Aaron, briefly. Aaron, what's the status of implementing this not on the Ising model, but for actual lattice quantum gravity? How is that progressing?
So that is progressing. At the moment, we are working through the intricacies of dealing with different types of simplices. So you have to create like a probability list of flipping each type of simplex, and there's 0, 1, 2, 3, and 4 simplices. And there's also the question of how do you update these simplices, because like the Ising model is a nearest neighbor interaction. We know which ones are going to get updated, but quantum gravity, we're not exactly sure which simplices need to get updated. So we're in the process of figuring that out and implementing it. But there is progress being made. I think we've gotten everything but the 4 simplices figured out, if I'm up to date with the work on that. And there's a graduate student, Ming Wei, who's working on that He's leading the effort on that one, implementing this.